So we're going to talk about a second set of classifications for robots. So some of these should be very familiar. You have your basic Cartesian. That's what a lot of these run in. Cartesian is using the XYZ methods. You have gantry robots. These robots are actually mounted overhead. There's a couple of different ways you can do this. You can mount some of these big arms overhead, and they have the ability to come down and do jobs. Or you can just have a simple pick-and-place gantry robot. But gantry essentially just means that it's an overhead crane type. You have prismatic, where it uses lines to designate motion. Swing, which is rotation around the robot base. Reach is the distance from the center of the robot to the furthest point in its workspace. So in other words, what is your reach where you're sitting? It's from the center of your body to the tip of your fingers. Does it make sense? And then you have SCARA. Now, this is a selective compliance articulated robot arm. We'll talk a little more about that here in a minute. All right, so work envelope or workspace, this is where the robot has the ability to do its job. Okay? So in other words, your workspace, your work envelope is from where you are to wherever you can reach. Right? Only difference between what yours and a robot's is a robot can't get up and walk off. Right? So essentially, your workspace in this room is the whole room. A robot's workspace is simply its area in and of itself. So we classify things by arm geometry, power source, path control technique, and intelligence level. And I'll say intelligence level is actually kind of a misnomer in this, simply because a robot has no ability to think for itself. We can give it the illusion of that ability, but we do not have the ability to give the ability for it to actually think on its own. It can make decisions very limitedly, strictly based on what is programmed into it. It cannot just randomly decide to do something. It has to have it pre-programmed. We're not going to talk about artificial intelligence. That's a totally different subject. So the whole reason we use a robot arm is to support the end of arm tool and to position the end of arm tool. It's the only reason it's there. It's there to move it. The robot is there to use a tool of some sort. Either it's using a gripper to move stuff, it is using a welder, a paint sprayer, something. But it's all about that attachment at the end of the robot arm. Does that make sense, guys? So 3 basic classifications. You have rectangular, otherwise known as Cartesian. These move in an XYZ pattern. Cylindrical, spherical. We've kind of talked a little bit about all these. So some other classifications is you have the SCARA, which again we'll see in here in just a minute. Okay. And some of the other terms you should use for the geometry, you can use Cartesian for rectangular, cylindrical is cylindrical, spherical can be also called polar, and jointed spherical can be revolute, just for some other terms that they can throw out there at you. So rectangular literally moves in a rectangle, cylindrical, spherical versus jointed spherical. Okay. So we have a couple of things that other ways we can classify these, and that's by the joints and what the joints do. So if the axis is a rotational axis, that means it moves in a circular pattern of some sort. That is a rotation axis. A prismatic axis is also known as a linear axis. None of these robots in here have a linear axis. They all have rotational axis. So a rectangular should have 3 prismatic axes or 3 linear axes. Why? Because they just move left, right, up, down, in, out. They don't have the ability to rotate anything. Cylindrical will have 1 rotation, 2 linear, or it's a RPP, R2P, whatever you want to call it. Spherical will have 2 rotational, 1 linear. Jointed spherical has 3 rotational. These guys have 6 rotational axes, guys. Does it make sense? Because each axis is able to rotate, it doesn't move in a true linear fashion. So for Cartesian geometries, you have 3 axes of motion. This is probably the simplest form of control. This is a very common one used, and it is as simple as it can be. Okay? It literally moves a square. How much easier can you get than moving a square? You can't. Often found in pick-and-place robots, it's used for material handling, machine tending, resistance welding, and can be used to do quality testing, inspection, adhesive bonding, and so forth. We can adapt any of these to do a different job. Their proficiency at that job depends upon your programming skills more than anything. So the advantages of this is that it's very simple and the control system is such. You can use very large work envelopes. If you're using an overhead crane, you can actually have that over a whole factory. And everything in that factory is that robot's domain. Does it make sense? This is a very, the most typical of them are overhead cranes that I can think of, or some form of a gantry robot. The disadvantages of it is that you have limited work envelopes because they can't be moved outside of their area. If you mount it overhead, the only way you're getting up there is with a lift of some sort. Response is slower in at least one axis because the actuator has to move the entire mass. And that is actually very true. I don't know how many of you have ever seen an overhead crane move. But in 2 axes, it can be very quick. It can drop that. We're talking about the overhead mounted cranes, the really big ones that go over a whole factory. What? These guys are mounted on rails over your head. And they have the ability to move from one side of a factory to the other. Yes, those are gantry cranes. For the really big ones, the movement from one side of the factory to the other is probably the slowest axis. Its movement from left to right is pretty quick, and its ability to drop the hook tends to be fairly quick. But if you're trying to get it from one side to the other with any kind of speed, you're going to be waiting a while. It's just made to pick and move. It can be used for other things, but it is 99.9% of the time seems to be used for pick and move. It can be used for machine tending and things like that, but a lot of the time it gets used for moving things from one place to another. Here's one right here. Again, you can see the rail it's mounted on. This one's got a rail, and it's able to go up and down on this rail. Let's see if I can pull this up real quick. This is what I mean by an overhead crane. These big guys. Their movement this way, so if we look at this picture in particular, their movement front to back is their slowest axis. Why? Because they're having to move the whole mass of that crane. The second movement is the ability for it to move left to right. That's pretty quick response time. And the ability to move that hook up and down is pretty quick. But let's see if I can get a really good picture up here of one of these. They can be, but typically you have an operator of some kind somewhere, simply because this thing can weigh thousands of pounds and you want to have hands on it. Something that's heading overhead of people that are down below, you don't exactly want you don't want to have it let go. Yeah. It's not something you just randomly let go and let it go. It's something you keep a hold of no matter what, because that thing can and will cause havoc. I'm trying to see. Most of the bigger pictures, you can't really tell what it's about. Doesn't show you a good picture. Here's a picture of an operator's booth on some of the bigger ones. So you actually have an operator's booth that's attached to some of these cranes. Huh? Yes, those can be used, but typically the ones you're thinking of are I think they're called boom cranes. The ones that have a big arm that actually come out like at an angle. That's a different kind of crane. These overhead cranes, yes, they can be used to load and unload, but their ability to do so is going to be limited by their work area. So yeah, they can only go so far. So that's a decent picture right there. So this guy can't move past the end of any of its axes. It can't overextend. So it might have the ability to, what you're thinking of, if I'm getting it right, would be that the ship would be right under here. You'd have two sides of the crane, and the crane would be able to unload the crates. The only problem I would see with that would be that you would have all your stuff just stacked right here on shore, and you'd have to have something else come in and move it again. And you want to talk about something that would take forever and a day. Cylindrical, you have things about like swing you have to worry about with this. We've already talked about reach. That's literally where you are in the center to where your fingertips are. And then stroke is the vertical and horizontal extent of travel. So this is a SCARA robot, and this is actually used quite frequently. He's actually quite a neat little robot. I'm trying to figure out where things are. He's quite a neat little robot. Um, so a cylindrical. Now the whole thing about anything that's got a rotational axis, no rotational axis actually runs a 365-degree turn. Why is that? Okay, so the question was, why does, sorry, why do none of the robots swing a full 360? Well, you could end up hitting the operator, but the biggest thing is you don't really want to. These have wires that are running all through them and all sorts of delicate mechanicals. You don't really want to mess with those and mess them up. That tends to be a bit of a very expensive oopsie. That's you've got to replace this whole thing. Yikes, kind of deal. So, just to kind of give you an idea on that. The way you know it's cylindrical is two axes run linear. They'll go in, out, up, down some way, but it has one rotational axis. Okay. So again, you have a cylindrical robot, and then you have what's called a SCARA. So that's a selective compliance articulated robot arm. So cylindrical, the advantages and disadvantages. Advantages is that you have a deep horizontal reach at the top and bottom of the work envelope. The singular vertical structure has the ability to reduce floor space, which in most places is that fairly important. What do y'all think? I was asking, sorry, why would a smaller floor space be important? Well, a lot of places you want to save space. A lot of that is because, yes, you want to be able to work in that space, but you also don't want it to take up your whole shop. Um, Space sometimes is at a true premium, and you don't always have the options to expand. Okay. Large payload machines are possible because of the rigid structures. That's why an overhead crane can lift about 10 tons very easily if it's put together correctly. It tends to be good repeatability for assembly instructions. Sorry. assembly applications, and you have the ability for quick arm movement and response. However, you do have a confined reach due to the limitations. Since you have it all on one rod, and that rod stands straight up, you don't have the ability for it to deepen the reach. Okay. All right. So primary uses for this. Machine tending is a big one for all of these. Pick and place is another for every robot. Those are the two biggest things that you see, along with welding and material handling. Assembly can be used for this. Arc welding and adhesive bonding. Adhesive bonding, what do they mean by that? What do y'all think? So with adhesive bonding, essentially, think about your car. Think about all the places they use to stick trim and fabrics and stuff like that. A human can end up with overspray, or they can end up without it coming in a neat layer. A robot can do it and just put it where they want it. Then you have sealing, grinding, and deburring. Does everybody know what deburring means? So deburring means that if you've got a piece of metal that's got any little sharp bits, it comes in and grinds all the sharp bits off. Okay. So you have a spherical arm geometry. This is one that's got two rotational axes, one linear axis. This is where, if you remember the Unimate, this is where the Unimate start. The Unimate was the first one. Okay. Used in only a few of today's robots because of the lack of versatility. It doesn't permit operation directly overhead or straight down. It limits itself. So this again, the Unimate, or at least what it is, closest approximation of it. Okay. So you have a horizontal stroke. That's the one linear axis, but everything else rotates. So advantages, it has got hours of proven performance in industrial applications, and has that long vertical stroke, but it requires a lot of floor space. Okay, and the arm has less flexibility than most others. Okay. Its main uses were primarily machine tending, material handling, welding, painting, and coating. So then we get to the jointed spherical. It's the one we think of as an actual industrial robot. Very close to what that is right there. So jointed spherical or polar is pretty much what we use a lot of. They're very versatile. The word articulated means that it's a lot of segments held together by joints. You have the very basic of these, which would be a 3 rotational axes. It's able to do almost a perfect sphere and is one of the most popular because of its versatility. Does that make sense, guys? Yeah? That these guys are extremely versatile. But all you have to really worry about whenever you're dealing with these is what kind of tool you're going to put on the end of that. Okay? So then you have the SCARA, which is the Selective Compliance Articulated Robot Arm. This guy gives a sweep movement. It has the ability to move horizontally. It has a vertical moving tool. And this guy actually produces a cylindrical envelope because of the way he rotates. He's a bit of a different cylindrical though, because most cylindricals have one rotational axis and then a vertical axis and an axis that moves in and out. This one moves in and out in a sweep motion, and the only way it can do verticals is through the gripper. Well, they call it a gripper, the end of arm tool. It's the only thing that actually moves up and down. So it's a little bit of a different one. So the jointed spherical polars, the advantages is that you have a very deep horizontal reach, a very minimum floor space, since it can fold up really well. You have a lot of positioning mobility with the tool, and you can have a lot of programming freedom. However, the controller is extremely complex, and it costs a lot more than the base robots. So everything's a trade-off in everything you do, just like life, right? So this one's the SCARA. Again, we've kind of talked about this by now. All right. I don't know who put this together, but they have got me all turned around to some of this. So applications for jointed spherical, material handling, machine tending, welding, of course. Those are the three base ones that you'll find most of these guys will do. Painting is another big one. Coding is a big one. Assembly is a big one. So when we talk about gantry, gantry robots can be as complex as actually mounting a robot to an overhead system. It can also be as simple as an overhead crane. But this gives it a seventh axis along a vertical or a horizontal plane. Then you have the Delta robot. This guy's a little bit like a spider-like robot. It's got 3 to 4 arms, and it gives it the ability to move up and down. It's in left, right, forward, and backwards. But it uses a dome-shaped work area. So we classify it by the drive power source. The most common power source for every robot is electricity. There are a few that use hydraulics and pneumatics, but most of them are powered by electricity. Okay? And that's because hydraulic drive power, it requires a lot to use. It has to have a tank. Think about the hydraulic systems in your car. You have to have a tank or reservoir of some sort. You have to have a pump to move the fluid. You have to have pipes and hoses to run it where it needs to go, as well as to return it back to tank, because that'd be messy otherwise, right? Control devices to make sure you can direct the flow and what it does, and then you have to have actuators to do the work. So hydraulics require a lot. The great thing is with hydraulics is that the power to size ratio is astronomical. think about it. You can use a car jack that the head of it is the size of your hand to lift your car that weighs about 2 tons. Your car or your truck. They can be used in explosive environments. They're very safe. However, they can have leaks. That's always bad. They're a bit of a fire hazard if the oil starts leaking out of it. You have to have a conversion of electrical energy to hydraulic power. You have to have some way to run the pump, right? And hydraulic anything is very, very noisy. Okay? Hydraulic anything is generally very noisy. Okay. Pneumatics, most of it's the same as hydraulics, only you don't have to have a return to anything. But you do have to have a water removal system, especially here in the South. Why? When? Summer is our enemy here in the South whenever it comes to anything mechanical, especially pneumatics. With pneumatics, you're generally using air from around you. Now, the good thing is that's a very cheap source of power. The downside is, here in the South, we suffer severe humidity, especially during the summer. That is the point in the year where you want to create gill slits in your throat so you can breathe fluid air. Because it's basically anytime you walk outside, you feel like you're breathing water. Okay? Um, that's good. So we have to have some form of a water removal system in pneumatics because otherwise you will end up with rust all over every component in it. You also have to inject oils back into it to lubricate your cylinders and such. Because if you don't do that, you're going to end up with a lot of wear and tear on them. That's the good thing about hydraulics. They tend to lubricate themselves. Pneumatics can't. So the advantage is pressurized air is readily available in most plants. There are very few plants around the world that don't have some form of a pneumatic compressor at hand. So factory conditions, a lot of them have a pneumatic compressor of some sort on site. So low cost and well understood technology backs this up. It's very fast operation. We use this very frequently for grippers and other tools. Air does not have to be returned to tank. It can be vented back to the air. And it is a very clean technology. However, controlling the flow rate for proportional control can be a pain. And if you over pressurize air, it actually can turn into a liquid in your pipes, thus causing other problems. So it's got its advantages, but it's got its downsides too. For any time you're using something like hydraulics, and especially when you're looking at using specifically along the lines of a pressure washer, PSI depends on the job you're going to do. With a lot of those, what you're going to have to look out for is you have to know what tips come with it, because the tips actually are what allow you to do the cleaning with pressure washers. When I mean tips is I mean they have different spray patterns, and those actually deal more with the pressure. Um, the actual unit has to build the pressure up. You're using the pressure through the hose. So just like your regular garden hose, the way a pressure washer works is you hook it up and you have back pressure created. And it's not until you pull that trigger that the pressure is released. Now, with a pressure washer, it has the ability to maintain the pressure you've built. So that always depends on the so if you're buying a pressure washer or anything like that, it depends on how big a job you're doing. If you're going to be doing, say, a whole house, you might consider something with a higher PSI. If you're just going to be doing the occasional driveway, you don't really need as high a PSI continually. Well, pressure washers, just like any other device, do break down over time. And that's just a sad thing about anything mechanical, is eventually it cannot maintain pressure and presence.
Yeah. Yeah, the only thing I'm trying to do is, a lot of people in the neighborhood, since it's gone to out, like one behavior, it's a cheap pressure washer, when they got the job done a little bit, and they ask me, they're like, hey, can you do like 20, 30 bucks? I'm like, sure, 20, 30 bucks.
So electrical power is the primary power source for just about everything. Some things can be powered by internal combustion, but even that produces an electrical power. So thus, this is what powers most of every controller. It's what powers most robots in some form, either directly or indirectly. You have to have electricity. So if you have an electrical drive power, which again is most of what a lot of robots run on, you have things that are called servo motors or stepper motors. You have ones that run on DC versus AC. So with all of this, we have rotational motors, which are rotary drive motors, and we have rack and pinion or ball screw for linear motors or linear motion. So the advantages of it is you don't have to convert the energy, which is really great. Operating noise levels are very low. You don't have a lot of hissing. You don't have a lot of noise that is in the background as things move. Direct drive models provide very quick response times. However, capability on the payload is about 300 pounds or less. And operation in explosive environments produces a problem, because if you've ever plugged and unplugged an appliance, you know that can cause a spark. Sparks are very bad in explosive environments, in case you didn't know. So yeah, electricity is both good and bad. But if you need something that's going to be a workhorse, power horse, you're going to need hydraulics. If you want something that works completely clean, you use pneumatics. If you just want something that runs, electrical. So classifications by control path, you have ones that are called continuous path robots versus point-to-point robots. So continuous path means that these are closed loop or servo systems, but the operator physically leads the robot through the motion to be performed. Let's see if this will come up. And the speeder moves are captured by the controller. This link will open. I'll let you see this. So if you notice, you got this guy and he's got a continuous robot. Now watch how he paints. He's trying to do the exact same movement every time. Now what's the bad thing about a human versus a robot? Is that huh? Robot will do the exact same thing every time. So if you notice, as he oversprays, he also does this little twist with his wrist. So watch his wrist movements in this and how he's controlling that robot arm. This is recording it just like you would record over an old videotape. He is. Hmm.
They're great at all those things. Ooh,
Yeah, they should be wearing PPE on this. You're correct. They're not. They must be in a very well ventilated area. So now if you watch how the robot does this, it's recorded every movement that he did. So even the little wrist flicks, watch it do that. It can do it faster than him, and it still gets that nice even coating, but any mistakes he makes, the robot will make. Yes.
Imagine if you just did a, like, look at that, and like, oh, it looks good to us, but the actual interaction, like, yes.
That's essentially what happens and why people have to go back and reprogram these. These are actually not as popular in the field as the ones that program point to point. These can be found and they are used, but again, if you have programmer error in any of this, you're going to find problems down the road. Okay? But like I said, you can notice the little wrist flicks that he was doing. The robot does the same. Why? Because that's how he was taught. Okay. So closed loop or servo systems is what we just saw. Distinguishing features is that the exact motion of the operator can be captured by the controller. The program length is specified in minutes of recording time instead of number of programming points, and it's usually not possible to edit or change a finished program. You have to go back and reteach it. It's stored on magnetic media such as cassette tape, disc. These days it's also probably stored on USBs and everything else. You consider the fact that I don't think cassette tapes really exist much anymore. So if that was continuous path, this is point to point. And that's that you have individual program points in the controller. Use a teach pendant to create the directions of everything. Okay? You literally give it point 1, point 2, point 3, point 4, and this is how you need to go through these points. You're able to set the exact path in the exact way the robot's going to move. So you have controlled path motions. This is where the axis moves at a speed proportional to the length of the move, and it moves in a straight line between program points. That's what we call a linear move. There's another move called a joint move, and this is where all your axis drives move at the same speed. And if X and Y distances are different, you will get an angle. You can also get some very, very funny, weird moves out of the robot. So a controlled path, it goes from point A to point B. But let's say it takes a non-controlled path. It could make a very different movement. So you have what's called a joint move versus a linear move. Another controlled path move is what's called a circular move. Those are the three main moves these robots are able to perform. So characteristics of both point-to-point robots. The programming does not capture exact motion of the operator, but you can edit the program as many times as you want, however you want. You can go in, touch up points, move points, and everything like that. And the programs require less storage. You can get precise arcs and straight lines between program points, and you have control of the tool center point during programmed moves, as well as the coordination of all axis motions. Intelligence level. So again, intelligence level, it's very much a misnomer. We call robots intelligent, but the fact of the matter is they only have a seeming of intelligence. They do not truly have thoughts and emotions and things like that. What they have is a facsimile of it through their programming and sensors. So we have a high technology level. These are closed loop robots. They require a lot of sophisticated programming and highly skilled operators and technicians to keep them running. Versus a low technology, which these are the open loop robots. These are the ones that have no what? What's the difference between open loop and closed loop, guys? Open loop has no feedback, closed loop has feedback. So it's either got sensors of some sort, it's got servo motors, it's got some way it is getting information about the environment around it. Okay? Low technology usually works with stepper motors, timers, or mechanical stops in order to get its motions correct. And that is that for today, guys, on that one. You have any questions on what we covered?